Hello everybody. Let us start our discussion on radiative transfer. Resume our discussion on radiative transfer. Last time we looked at a few concepts. We talked about the specific intensity of radiation. Let me remind you of these things before we proceed. This was written as I knew. Remember, this is a function of the direction in which you are looking at. And this is energy passing per unit area of a detector or per unit area of any area that you have put in the path of the radiation, per unit time, per unit frequency interval, and in a solid angle around the direction n cap. We also defined specific energy density of radiation. So this is also a directional quantity. You are asking the question that if the energy is going in a direction n cap, then what is the specific energy density? This is how much energy is there in a given volume and per unit solid angle. These quantities are related. U nu n cap is I nu n cap by C. And if you consider U nu integrated over all directions, that is related to the average specific intensity, average over all direction in this way. So these are the relations that we learned last time. We also saw if there is no medium between the source and the observer, then specific intensity is something that does not change with distance from the source. So this quantity is zero. There is no change. So S, remember, is the distance from the source. This is what we done in the last discussion. What we will do today is to see what happens if I have a medium present. So let us start our discussion today. What happens if there is a medium? Okay, so that is the question that we are going to ask today and find the answer to. So what is the picture? The picture is that I have some radiation coming in. This radiation at the source, this is I nu. Okay. And then I have a medium, some medium here. And after the medium, I want to know what will be the radiation here. So, what is this red I knew? That is what I want to know. Okay. In between the medium, two types of processes grossly can happen. One that depends on I knew, and the other that does not depend on I knew. Okay. So we will see the effect of both of these processes today. So let's start with processes that does not depend on I knew. So process that does not depend on I knew. So I'm calling background because it's kind of coming from behind the medium. So background specific intensity. Okay. Now today onwards, whenever we will talk of radiative transfer, we'll only think of one dimensional radiative transfer. So this is 1D radiative transfer, which means that I can only ask the question, or I will only ask the question when the change is along one direction. Change of intensity is along one direction. So this direction will use the usual thing used in literature is s, small s. So we'll also use small s. So as s increases, s equals to 0 here. So if this is my source, here I have s equals to 0, and s increases as you go right hand side. And that is the only direction in which we will see what happens. So this is an example or a problem of one dimensional radiative transfer. Of course, radiative transfer is not always one dimensional, and there are a lot of complications that comes in once you consider multidimensional radiative transfer. A bunch of astronomers work on that problem, and it turns out to be extremely difficult problem, and people are still trying to figure out efficient algorithm to tackle that problem. So you can see that obviously in this course we cannot go at that complicated level. We can only talk about the simplest case, which is the one dimensional radiative transfer. Okay, this problem was first addressed, and what we will going to derive today was first done by Carl Schwarzschild. He's the same person who is responsible for giving the first analytical solution of Einstein's equation in general relativity, which is the other thing of him that we'll learn. He did not live for long, otherwise, we would have probably had a lot of interesting stuff coming out of him. Anyway, so what is an example of a process that does not depend on the background radiation? What is that we are talking about? We are talking about some process that essentially either adds or subtracts things from the background radiation. Well, now, if you have to subtract something from the background radiation, it has to depend on the background radiation, because otherwise, how will you take out of it? But you can always add, independent of knowing what is coming from the background. Adding something to the radiation is called emission. So this essentially is what we are talking about is emission. So we are talking about atomic radiators or molecular, or I mean simplest model is atomic radiator, some type of radiating element inside this medium. So this was my medium, right? So inside the medium, there is some type of radiating element which is present, and that is adding to the radiation. And this radiation, this emission is not provoked by the source radiation, that is the regime that we are talking about now in this column. So these are called spontaneous emission. And you may already know, and you will also learn later, that there can be emission which is stimulated by the incoming radiation. Those we call stimulated emission. Einstein was the first person to talk about it, and that does not fall in the category where the process doesn't depend on the background radiation. So here we are talking about spontaneous emission. Okay, so let us ask the question: how will my intensity change if there is spontaneous emission in the medium? What are the assumptions? Obviously, we cannot deal with a very complicated situation. So we take the following assumption. Assumption is that the emitters are isotropic. Emit isotropically. So it emits same in all directions. It doesn't know which direction it will emit more. If you have studied the emission from an electric dipole, you know that it doesn't emit isotropically. So it emits more in some direction it doesn't emit at all. But here we are assuming that the emitters are emitting isotropically. If it is like hydrogen atom going from one state to the other state, electron jumping from one energy level to the other energy level, then on gross it will be isotropic, because different hydrogen atom will be oriented different way, etc., etc. So because of that, you will get isotropic emission. So that is not a very bad idea. So you can see that obviously the dipole type of radiation is not isotropic. So here essentially we are talking about kind of atomic emitters. Or if you have many dipoles, then the dipole orientations are random, then also this will be satisfied. What will this depend on? How much emission is added? So what will that depend on? Obviously, it will depend on the number of emitters per unit volume, and it will depend on what is the total volume, because then that will give you the total amount of emission that has happened. So it will depend on this and the total volume, as simple as that. Okay, on the if I want to draw a picture, say this is and I'm drawing a cylindrical volume for no reason, can be of any size, but remember that our radiation is going in this way. Here it was I nu. Here, because I'm talking about emission, it has added a little bit to that I nu, and say my volume is having an area delta A, and this cross sectional area is delta A, and the length of the volume is like delta S. Okay, so that is the picture that I have in my mind. So if I ask the question volume of emitters. So this is equals to simply delta A times delta S. Okay. Now, how much emission will happen will depend on which atomic process I am talking about and how much that atomic process gives emission in the frequency range nu and nu plus d nu. Right? So we have to define something that characterizes such processes. So we call it specific emissivity. And you know why it is called specific. So I denote it, usually it's denoted by epsilon and suffix nu for specific. This is spontaneous and isotropic energy emission per unit frequency per unit time and epsilon nu is defined as per unit mass. So per unit mass, this much of emission has happened per unit mass of the atomic emitter. So if I ask the question now, energy emitted the energy emitted is same as the energy added, but let us keep as energy emitted for the time being. So energy emitted per unit volume per unit frequency interval per unit time. I'm writing shorthand for the time being. How much will this be? So the only change I am doing from epsilon nu to here is that instead of talking about per unit mass, I want to talk about per unit volume. How do I do that? Well, there are rho atoms per unit volume. There is rho mass per unit volume. So rho is the volume density. So this is what I want, where rho is the mass density. And if I want per unit solid angle, what do I have to do? Well, epsilon nu is isotropic emission. So it's the total emission going out in all direction isotropically. So if I want to know how much is going per unit solid angle, there are 4 pi solid angles. So I need to divide this by 4 pi. Now this quantity has a name. It's called J nu. Spontaneous emission coefficient. So what is its definition? Its definition is energy emitted by these atomic emitters per unit volume, per unit frequency range, per unit time, per unit solid angle. So that is shorthand written as J nu. but it's the spontaneous emission coefficient. Okay, so that is the count for the energy. So can we now ask the question that what is the intensity for this emission? Okay, so for that, let us first say that what is the total energy added. So total energy added if I call it delta E added, what will it be? Well, I can write in terms of J nu. J nu is energy emitted per unit volume. Remember that how much is the volume? The volume was delta A times delta S. So we are talking about energy added in this cylinder and the path of the radiation, right? So the energy added is this times the volume, which is delta A times delta S. Per unit frequency, so if the frequency interval is delta nu, so then this is in delta nu frequency interval, this much is added. If the time interval is delta t, in that time interval, this much is added. And finally, I have to multiply by the solid angle. So this is the energy added. So this energy added will give rise to the excess intensity over here, right? Because that is the radiation energy, that is the count of the radiation energy in terms of specific intensity. So what will be delta I nu? So delta I nu this is because of spontaneous emission, will be the energy added, and we know how to define delta I. This is per unit area, per unit time, per unit frequency interval, and per unit solid angle. So it gets divided by delta A, delta nu, delta T, and delta omega. So I'm left with this J nu delta S. So you see, it depends on how much it has traveled and the spontaneous emission coefficient. I can even write it in a differential form. So if I have only spontaneous emission, I get a differential equation of I nu, which looks like this. Remember previously, when there was no medium, the right hand side was 0. Now, the spontaneous emission coefficient is there in the right hand side. So this is our second incarnation of the radiative transfer equation. So one-dimensional radiative transfer equation is nothing but how I changes with S. So initially we saw when there is no medium present, then it does not change. Now, if there is a medium and only one type of process is happening, which is that depends on the does not depend on the background does not depend on the background intensity, then what I will get is a change. Now I will see a change of I nu as it progresses through that medium. The much it progresses, the much the I nu increases, and the increase per unit length is given by the spontaneous emission coefficient. Okay. Obviously, we still do not know how to write down spontaneous emission coefficient J nu in terms of the processes that will give rise to it. But that obviously will depend on the processes, and we'll see one example of it in future lectures. Okay, so this is all about when the mechanism that adds or subtract from the radiation inside the medium does not depend on this incoming radiation. So now let us, so this is this case, process that does not depend on the background ion. So let us come to the case where the process that depends on the background ion. Process that depends on the background, So what comes into mind? One comes into mind is absorption. That is, if you have a lot of photon coming in, then it may happen that they collides with some of the atoms in the medium, and then that atom engulfs the photon. Like if it's a hydrogen atom, it takes the photon and takes one of its electron. The electrons changes its orbit. So because of that, or energy level, because of that, the photon gets absorbed. It can be like photoelectric effect, also that the photon get absorbed. But there is another process which is called stimulated emission, where if a photon of frequency nu falls into the atom may give rise to a radiation in frequency nu, and it will double the number of photons. So that also should be counted here. So that's called stimulated emission. And this is a type of emission that depends on the background radiation, was first coined by Albert Einstein in 1905. Now, for this discussion, we'll only think about absorption, but what we will do also apply for stimulated emission. In fact, when we'll take up a concrete example and try to figure out what are these emission and absorption coefficients. Absorption coefficient I have not defined yet. We will define it shortly. Then we will see that that coefficient incorporates both absorption and stimulated emission. Nevertheless, for this discussion, sake of understanding, we only consider absorption. Okay. So let's see what is the picture. The picture is the following. Again, let me draw this medium a little bit bigger this time. So this is, say, my cylindrical shape of the medium, the incoming radiation coming from here. So this is I nu. Inside, something is happening which will come to, and then the radiation comes out from this side. And because we are talking about absorption, there is a little bit lost in the medium. Okay, so the change is negative, if you wish. The output minus the input is negative, which is minus delta I mu. And again, just like before, let us consider that this distance is delta S. Now, when I talk about absorption, these photons of the incoming radiation must be interacting with the whatever is absorbing inside, and that interaction of absorption happens over an area. Strictly speaking, it is not like that. It may happen. So when I say over an area, I mean that it's not only that pinpoint atom at which this interaction happens, The photons see an atom projecting a finite area. And we are essentially talking about an effective area. This thing I will write as sigma nu because a photon of frequency nu will see a certain area which is called sigma nu. This quantity inside it hides many things like what is the process of this collision, what is the probability of that process to happen, etc., etc. But it is written in terms of a single quantity, usually noted as sigma nu. This is called the cross section. In quantum mechanics, you learn how to calculate this cross section of different processes. So this is called the cross section. Okay. So if there is an atom like that, and you see the atoms are actually rare in the medium, or it offers it. So if this is the cross sectional area of this entire medium is capital A, which is what, or delta A, as we are writing before, this sigma is much smaller than that. And if you consider all the atoms, in most of the cases also, most of the places in this volume is empty. Okay, so that's a very good approximation. You know that there is the interatomic distances even in solid is quite large compared to the size of the atom. So if I ask the question, what is the volume offered by such single atomic observer, to the incoming photon? So if there is one photon, this volume is 1 into the area is sigma nu, and it can happen anywhere in this. So that is the total volume. So sigma nu times delta S. There are n photons. So the first photon come, hits, gets absorbed. The second photon can still come and hit and can still get absorbed. So for n photon, this is just n times sigma nu delta S. But this is by a single atomic observer. So if there are n atoms or n atomic observers, per unit volume, then number of absorptions in the medium. In the medium means in the medium that we are talking about, that medium of length delta S, the cross sections are sigma nu, etc. And if I have n incoming photon, What will it be? One atomic observers, sorry, one atomic observer gives you these many collisions. So if there is n atomic observer, it will give you these many collisions. So if there are these many collisions, these many absorptions, these many photons will be lost. So if I write delta n, so this is the number of absorption. So let me keep it like this. So these many photons will be lost from the incoming photons, right? Now the intensity, which is a measure of the radiation falling into it, obviously depends on the number of photon inside that in that producing that intensity. So the intensity is directly proportional to the number of photons. So the fractional change in photon here, fractional change in number of photons what will this be? Fractional change is change with respect to the original number. The original number is n, so the fractional change will be n sigma nu and then delta s. Now the fractional change in the number of photon will be same as the fractional change in the number of in the intensity, because the intensity is just the number of photons is higher if the intensity is higher, right? I should write a minus sign here because this change is negative, it decreases. So now I can write di nu by I nu, directly writing in differential form, equals minus n sigma nu ds. And here is our definition of absorption's coefficient. And obviously specific per unit frequency range. So this sigma nu times n is the absorption coefficient, which we call as, alpha nu. Okay. So this is the absorption coefficient. The emission coefficient is J nu, and the absorption coefficient is alpha nu. So I get a differential equation. So if there is only absorption and in the medium, so when I say only absorption, I also include spontaneous emission inside it, because they are almost the same process. This coefficient will be negative in case of spontaneous emission because it is adding up to the radiation. But mathematically they are the same thing. So my radiative transfer equation in case of only absorption, as you can see from top, is minus alpha nu I nu. Okay. So what have we got? We have got, let me recapitulate. So if there is no medium, I nu doesn't change with s, di nu ds equals 0. If there is medium and only emission, then per unit distance the radiation travels in the medium, J nu amount of intensity is added to it. So d I nu ds equals j nu. J nu is the spontaneous emission coefficient. And if there is absorption, then minus alpha nu I nu is taken out per unit distance the radiation travels in the medium. So if I have both emission and absorption present, it is straightforward to write down what will happen now. This case, the radiative transfer equation will just have both the effects. So d I nu ds is j nu minus alpha nu I nu. So that is the full radiative transfer equation in one dimension, first done by Carl-Schwarzschild. Its form was a little different, but essentially the same thing. Okay, so before we leave today, let us try to analyze this a little bit, and then we'll try to write it down in a little different form, which is more useful in astronomy. To do that, let us go back to the case of only absorption and try to solve the equation. So I have a source here. So this is, I call S equals to 0. And then I have medium everywhere, say. This is my medium. And S increases this way. So if I write I nu, at this point it is I nu at S equals to 0. And when I try to calculate at some S, so that is I nu at that S. And I have only absorption. So my radiative transfer equation is d I nu ds is minus alpha nu I nu. Okay. So let's try to solve. Remember that alpha nu, what is alpha nu? This is the number density times the cross section. It can change along the medium. There can be different types of processes along the medium which will change sigma nu, and there can be different number densities along the medium which will change n. So it can be different along the medium. So alpha nu is also a function of S. So how do I solve it? So I have d I nu by I nu. This I integrate from S equals to 0, where I nu this is at S equals to 0. And here it is, say, I nu at S. So I should have primes here. In the right hand side, I have minus S integrates from 0 to S. And I have alpha nu, and customary to write in terms of prime inside, ds prime. So what will you get once you do the integral? Left hand side is log, so it is ln I nu S by I nu. So let's write this. For this, let us write short form, which is I nu 0. In the right hand side, I get this. Now, this quantity I define as tau nu S. Or let me define it the following way. Okay, so tau nu is something that also changes along the path. So just like S changes, the other thing that changes is tau nu. Now let me tell you what tau nu is called. It has a name, it's called optical depth. It's a very useful concept, particularly in astronomy, and we'll come back to why it is called optical depth. But let's see what we have got here. So if I integrate this, obviously I will get minus tau nu. So then I can rewrite this solution as, this is, remember, when there is only absorption, this is I nu 0 e to the power minus tau nu. So absorption gives attenuation. What do I mean by attenuation? It means that it not only decreases, the intensity decreases because of the absorption, it decreases exponentially as some quantity called tau nu, optical depth, increases. Okay. So if tau nu is much greater than 1, then I nu at S will almost be 0. If tau nu is very small, then I nu at S will be almost I nu 0, maybe a little less. Why is this an important concept? You see, the amount of attenuation not only depends on the absorption coefficient. The absorption coefficient may be very low, but if you, in such a medium, if you travel, the light travels for very long distance, then also you will get a very large attenuation. And vice versa. If the absorption coefficient is very large, the light may travel only a little bit in that medium, but it will completely get absorbed. Like, for example, if I have a fog, the light has to travel a lot before it gets enough absorbed and it doesn't reach you. It travels few hundred meters and still it will not be able to reach you, because it has traveled few hundred meters, and many of the photons will get absorbed of a source and finally will not see it. On the other hand, the same absorption can happen if I just put a black cloth in between source and the observer. That black cloth has a very small thickness, but still the observer doesn't see the source because it's kind of what we call opaque. So this quantity tau nu essentially measures how much total absorption is there. So it's called optical depth. But it also has another name called opacity, just because it tells you how much opaque is the medium. Or how much transparent. They're just the opposite thing. Okay. You see, for alpha nu ds I wrote d tau. So d tau was alpha nu ds. Right? This was how we introduced tau nu. What we can do is, I have the radiative transfer equation. Let me write it here. we can write the radiative transfer equation instead of a differential in S, I can change it to differential in tau just from here. So what will it become? So this is now I am trying to write down the radiative transfer equation. In terms of the optical depth. So what is this? I replace ds by d tau, so I get a alpha nu ds. So I get alpha nu in the numerator and then ds. So what I do is I divide everything by alpha nu. So with this much of manipulation, which is extremely easy to do, so I will not do it for you here. You will see, you will get j nu by alpha nu minus I nu. The other way of writing it is again defining something new now. Which is S nu it's nothing but j nu by alpha nu. This is called the source function. You see, what does it depend on? It depends on the ratio of the emissivity to the absorptivity or absorption coefficient. Emission coefficient to the absorption coefficient. Both emission and absorption depends on the source. So that's why it's called a source function. So I'll stop here today and we'll start by looking at a more general solution of the radiative transfer equation. And what are the different types of radiations? What do we mean by thermal and what is non-thermal radiation? And consequences of that.